Okay, welcome to AP Chemistry. And I have a couple of students with me, and we are going to start in the middle of the packet on 2001. And so if you're looking at those 5 solutions, our first question is to identify a pair of the solutions that would produce a precipitate when we mix them. So what are you looking for? Yes, I'm calling on y'all. What are we looking for when we are trying to pick which reactants produce a precipitate?
You're looking for something that does not have a group 1. You're looking for one that does not have. You're looking for a pair that does not have both a group 1 and or the big molecule.
Okay, so you're looking for things that you have some things that are not soluble, and when you mix them, you'll form something that will precipitate out. And if we look at solution 1 and 2, when you mix those two guys,
is KMNO4 programmable?
no, K forms the ion, and then manganate is a negative ion.
So like then why wouldn't it be 1 and 3?
Why wouldn't it be what?
1 and 3. Does PBMNO4 not 1 and 4 not precipitate? And how do you know that?
You would have ones that are always going to form the ones that you know. So this is from 2001. This is from 2001, and there are actually 2 answers. So the first one is solution 1 and 2. Okay, the other one is, and I'm just going to finish this one because this is probably the most common answer. If you mix those 2, what precipitate do you form?
PbCl2.
PbCl2. And so that is our precipitate. Now, the other answer that was accepted is solution number 1 and solution number 3.
Okay, so
If you look at solution 1 and solution 3, PbNO3, when those 2 react, you probably didn't have this one, but it actually undergoes a redox reaction, and the permanganate ion forms an MnO2. Oops. So if you selected 1 and 3, that would also be accepted. So actually,
so you would have to get the precipitate.
yeah, you have to give the precipitate. So it was easy to get. This is 1 point for picking the 2 solutions that produce a precipitate. So either 1 and 2 or 1 and 3. The other point would be for naming the precipitate. Now, if you picked the permanganate ion, that point's harder because you have to know that reaction. I will say your choices will be a little bit different because your rules are different than they were in 2001. So if you can pick one based on the rules that you know, you're good.
Thank you.
You're welcome. Which solution would be the least effective conductor of electricity?
Solution number 4.
Okay. Solution number 4 is the right answer. Why?
It doesn't have a group 1 or it's ammonium or nitrogen.
Yeah. It's actually the only one that doesn't form ions. Doesn't form ions. All the rest are ionic compounds. How do you know if it's an ionic compound? So if you're looking at the other ones, all of the other ones are ionic. And if you look at those, they all contain a metal plus a nonmetal. Solution number 4 is the only one that's completely covalent. And that one is actually ethanol. Okay, now let's look at 2004. So a little bit further in the 2000s. Now we have a question related to the solubility. So if we look at silver chromate and silver phosphate, there was a question in 2004 about those, and we have just one part of that question that is write the balanced equation for dissolving silver phosphate in water. So if we come over here, let's look at that. If I want to write the equation for dissolving silver phosphate in water, what do I do? How do I start?
Silver phosphate.
Okay. Silver phosphate.
Plus water.
Okay. And we don't even have to do plus water. It's just kind of understood that the water's there. What happens to it when you put it in water? It what? Yeah, it breaks into the ions. It dissociates into Ag plus 1 and what's the other one? PO4 minus 3. So we have phosphate and we have silver. Are we good? Yeah. Last step, we do have to balance these. It says the balanced equation. And so if we put a 3 right there, we are balanced, and that was worth a point. Okay, moving on. 2007. So in 2007, there's a problem about number 5 is the mass percent of iron in a soluble iron 2 compound. And it's measured using a titration. And so we found how much iron is in that compound by titrating it with this manganate ion. And so the first question has to do with what is the oxidation number of the manganese in the permanganate ion. So if we look at that permanganate ion, what's the rule?
I should always be a -2.
Okay, so if we look at that, this is an ion. So all the oxidation numbers, when we add them up, will equal what? It's going to equal -1. Now, oxygen, we have some rules about oxygen. It's not bonded to fluorine. If it was, it would be a +1. It's not a peroxide, then it would be a -1. It's not by itself, then it would be 0. It's not those 3 exceptions, so it must be what? Yeah, it must be a -2. And we have 4 of them. So 4 times -2 gives us a -8. And so the manganese will have an oxidation number that when we add it to this -8, it will equal -1. So the manganese must be what? +7. Okay. And that was worth a point. That is all you need to write. Okay. Then the next question says, Identify the reducing agent. Now, if you look right here, it says the reducing agent is oxidized. So we're just looking for what is the thing that's oxidized above. So let's check out the things above and figure out which one's being oxidized and which one's being reduced. So if we look at this, we'll start with the iron. The iron goes from a +2 to a +3. How does it do that? Yeah, it loses 1 electron. And if you lose electrons, that's oxidation. So I think we found it first shot. So our iron 2 is a thing that is being oxidized. And our things that's oxidized is acting as our reducing agent. Okay. So the next part of this is a little bit wordy. And let's look at this. It says we have that sample of iron 2, and it's measured, and it's dissolved in water. It's acidified, and so it will react. And so this solution is then titrated with the permanganate until the end point. And at the end point, that means that all of this is used up. So the next part is not a question you would maybe have now. You might have this when we get to acid bases, just about indicators in that unit, but I left it in because it doesn't hurt to talk about it. It says describe the color change that occurs in the flask when the end point of the titration has been reached, and explain why the color of the solution changes at the end point. So if we look at this reaction, let me clean this up a little. What you might have is you might have that this is colorless. This one is colorless. This one is a very dark purple. This iron 3 that you formed is also colorless. This one is colorless. And so it says describe the color change that occurs when the end point has been reached and explain why the color changes at the end point. And so what happens is, I'm going to hop down at the bottom for part C. So for part C, if we look at that, the purple permanganate ion.
If you drive a white Civic and or a blue GMC Sierra and are still parked in the bus loading area, you need to move your vehicles immediately. Ethan Falcon and Savannah Walker, please report 2 vehicles to move them.
Okay, sorry about that. So the purple permanganate ion, as it is added, reacts and that resulting solution is colorless. The resulting products are colorless. The end point is when some of the purple permanganate is added. And a pink color. So when we add the purple permanganate, you have a pink color in the solution. And what that pink color is, it's just a really dilute purple. So that's how you could be asked that question now. But let's look at D. If we look at this, we are supposed to answer this question for this titration in terms of G, which is the mass in grams, capital M, which is the molarity of the permanganate, and then capital V, which is the volume. And so if we're looking at this, we want to know what are the number of moles of iron in the sample. And so if we want to know the number of moles of iron in the sample, that is that iron 2 that we're looking for. And so how would we figure that out? We'd use the variables.
Make the t-chart being the starting point.
Okay. So if we look at what we know, let's go back up and look at what we know. We know the mass. Okay. So our answer is going to be in terms of these three variables. And so if we look at the grams, if we want to know the moles, and we want to start with G, what would we need to know to use that? The molar mass. Do we know the molar mass? Okay. Well, I know the molar mass of iron, right? 55.85. But we don't know the molar mass of our compound. And this G is for the compound. We know iron's in the compound. We don't really know the other things. So that is why we can't use G. So if we go to the next one, we know the molarity of the titrant. We know the molarity of the permanganate. And we know the volume of the permanganate to reach the endpoint. And if you read that in terms of these, it says the number of moles of the permanganate to reach the endpoint is M times V. So we know the moles of MnO4 equals MV. So knowing that, I would like to get the number of moles of iron in the sample. If we know this, could we get to moles of iron in a sample? How would we do that? And so I'm going to come down here. Unfortunately, the reaction is a little bit higher than I wish it was, but if I want to know the number of moles of iron, what if I start with the moles of permanganate? Because from the information given in this paragraph right here, I know that. And I know that all of this reacted with the iron until it was all gone. That's what the endpoint means. And so I can go from moles of MnO4 to moles of iron, moles of my iron compound. And how would I do that? Mole to mole ratio. So let me go back up to my balanced chemical equation, and I am looking right here. I have 5 irons reacting with every 1 permanganate ion. So these guys are in a 5-to-1 mole to mole ratio. Now, I'm not supposed to do it in terms of this, but I can say that in terms of M and V. So I know that moles of, let me circle it in red, moles of MnO4, or moles of my permanganate, are actually, look what we set up here, M times V. And then if I multiply it by 5, which is from my mole to mole ratio, I know my number of moles of iron in that sample. So if we look at this, we have our reaction again, except now we have to find the mass of the iron in the sample in grams.
This time you're going to be using G.
So this time, maybe, we want G, we want the mass in grams. So knowing what we know, how would we get there? From what we just did.
Would we start out using the moles and then work with the grams?
What?
Start out using moles and then work with the grams.
Exactly. So in the last part, didn't we just find the moles of iron? Now we know the moles. Now we can figure out how many grams. So if we start with what we did in the last problem, and in the last problem, what was it?
M times V times 5.
M times V times 5. So that is the number of moles. And then how would we get the mass of the iron? So if this is moles,
Make the chart and put
and put what?
1 mole.
1 mole. 1 mole of, okay. What? Yeah, the molar mass, 55.85 grams. And so that answer, that is the answer. You could just write that. So we would have 55.85
Good afternoon.
times
students.
5
Seniors, orders for caps and gowns and graduation supplies will be taken on
times
Thursday,
M
October 18th.
times V.
Class of
How would we find the mass percent of iron now? How would we find the mass percent of iron?
Would it be 55.85 divided by what we just got?
We want the mass of iron of iron in the sample divided by the mass of that whole sample, the mass of that whole compound. But we have to write it in times 100. So that's the part that's iron over the whole, that's the compound. And so didn't we just find this one? So we can just write that, 55.85 times 5 times M times V all over, what's the mass of the compound? So if we look back up there, that is G. If you multiply that times 100, then you have the mass percent of that iron. You have the part that's just the iron over the mass of the whole compound, the whole sample, times 100. Okay, and then the last part says, what will adding too much titrant have on the determined value of the mass percent? Well, if you add in too much of the titrant, I'm going to, in blue, if you add in too much of the mass of the titrant, you add in too much of the permanganate ion. So this number right here, the volume, is too large. And if the volume is too large, isn't your whole mass percent number too large? So if the volume is too large, it makes the calculated mass of iron too large, and the mass percent too large. Okay. In this part, 1 point was earned for this answer. In this part, 1 point was earned by dividing the previous answer by G, another for multiplying by 100 to get percent. 1 point for this answer, and going back to this one, 1 point for this answer. And that's the end of our video.